Electromagnetic Induction. In this video, we'll be covering magnetic flux, electromotive force, Faraday's law, Lenz's law, and eddy currents. Magnetic flux is a measure of the change in magnetic field through a certain area. It is defined as the product of the magnetic field strength and the area perpendicular to the field. This symbol here is the Greek letter capital Phi, and you can see here the magnetic field times the perpendicular area of the magnetic field can also be written like this, where theta is the angle between the area and a line perpendicular to the magnetic field. The units of magnetic flux are Weber. It is important to note that this is not the strength of the magnetic field, however, is representation of the change in magnetic field when, for example, the magnet is moving. When a magnetic field is moving in relation to a conductor, a potential difference can be induced. If this conductor is a closed circuit, a current can flow. This is known as electromagnetic induction. A potential difference is induced when the magnet is moving in and out of the coil. No potential difference is induced if the magnet is stationary and there's no relative motion between the two. And the direction of the induced current depends on the motion of the magnet. You can see on the diagrams on this slide that when the magnet is moving towards the coil in this situation, the magnetic flux increases as the field lines here are a lot closer than they are further away from the magnet. When the magnet moves away from the coil, like in the other example, the magnetic flux decreases. So this change in magnetic flux in the coil induces a potential difference in the coil. This is referred to as electromotive force. I'll cover this in more detail later. However, you can see when the magnet moves in and out of the coil, this current is induced in the coil. The electromotive force is equal to the rate of change of the magnetic flux, and this is known as Faraday's law of induction. So the change in magnetic flux divided by change in time is the electromotive force. When we have a situation where there's multiple loops, such as in a solenoid, the electromotive force is induced in each of the coils. So the formula for Faraday's law for a solenoid becomes this, where N is the number of coils. Russian physicist Lenz was investigating Faraday's law. Lenz noted that the induced current always flowed in a direction that produces a magnetic field that opposes the magnetic field that created it. And this is known as Lenz's law. So looking at the example on the left here, the magnet here is entering this coil and the magnetic flux is increasing as the magnet goes towards the coil. This is because the density of the magnetic field lines here is greater. Now, the magnetic field that opposes it points in the opposite direction. So that's what these pink arrows are here. And if we use our right hand rule, our thumb will point in the direction of the pink arrows, our fingers will point in the direction of the conventional current moving in the coil. Comparing it to this situation here, on the other diagram, the magnetic field is moving towards the right. The opposite magnetic field will be pointing out the opposite direction. So using our right hand rule, our thumb will be pointing to the left and our fingers will be pointing in the direction of the conventional current in the coil, which will be this way here. Also, if the magnet is moving in the opposite direction, the magnetic field is changing, so the magnetic flux exists. The magnetic field that opposes this change will be in the opposite direction, this time to the left in this diagram. And what that means is that the current will be produced in the opposite direction to before. And if we move it in and out, we have an alternating current. Now, the electromotive force induced by the change in magnetic flux is a source of electrical energy. Now, energy cannot be created or destroyed. This is the law of conservation of energy. So for energy to be conserved, there must be a source of input energy that is transformed into the electrical energy. So Lenz introduced a negative symbol into the formula for Faraday's law that indicates the electromotive force opposes the change in magnetic flux. So we've looked at examples where the electromotive force induces a current in a coil. However, this current can be induced in any conductor, such as a flat plate or tube. In these cases, we refer to the currents as eddy currents, as they swirl much like eddies in water. So an eddy current is a current that is induced on a flat plate or a tube due to the changing magnetic field. So let's look at a situation where we have a flat plate on a pendulum that swings through a magnetic field. You can see in the diagram that the magnetic field is going into the page, and the flat plate is just a conductor, nothing special about it. Let's look on the left-hand side as the plate swings into the magnetic field. As it enters the magnetic field, the magnetic flux increases and it sets up an eddy current in the anti-clockwise direction. So we can use our right-hand rule to find that. If the magnetic field is into the page, the magnetic field that opposes that is out of the page. So what you'll have is your right hand thumb pointed towards you, and the direction of the fingers will be the direction of the current. So curling around anti-clockwise. And that's what it says in this diagram here. So as the plate enters the field, it's only the right hand side of the plate that's in the field. And if we use our right hand palm rule, the direction of the current right here is pointed in the up right direction. Our fingers will point into the page because that's the direction of the magnetic field, which means our palm points in the direction of the force. And this is unbalanced because the other side of the plate is not in the field yet. So there is a force that's in the opposite direction to the plate's velocity. So just as it enters the field, the plate will slow down slightly. When the plate is completely inside the field and the field is uniform, there's no changing flux, so there is no eddy current induced. Now we can look at the similar situation when the plate exits the field. In this situation, it'll be the opposite effect. So the eddy current as it exits the field will just be on this left-hand side, and the force will be in opposite direction to the velocity, so again slowing it down. So this plate in this situation, due to the eddy currents, will slow down as it enters and exits the field. As this magnet is moving to the right into the coil, which direction does the induced magnetic field of the coil point? Which direction will the conventional current flow? And which direction will electrons flow?